For decades, Hubble transformed astronomy by staring deeply into tiny regions of the universe.
Now NASA has built a telescope with a similarly sized mirror, but a view at least 100 times larger.
Its name is the Nancy Grace Roman Space Telescope, and its mission is to survey the universe on an unprecedented scale.
NASA currently plans to launch Roman no earlier than August 30th, 2026.
It will search for invisible matter, mysterious cosmic energy, undiscovered planets, and events nobody has ever witnessed. This is the telescope designed to give humanity its first truly panoramic view of the infrared universe. Roman is NASA's next flagship astrophysics mission, built to explore everything from our solar system to the edge of observable space. The observatory honors Nancy Grace Roman, NASA's first chief astronomer and a pioneer of space-based astronomy.
Her leadership helped make Hubble possible, earning her the enduring title, the Mother of Hubble.
Originally called the Wide Field Infrared Survey Telescope, the mission was renamed in her honor in 2020.
Roman's primary mirror measures 2.4 meters across, the same diameter as Hubble's main mirror.
But Roman can record a region of sky at least 100 times larger in a single exposure.
NASA expects Roman to survey the sky up to 1,000 times faster while maintaining comparable infrared resolution.
Fully deployed, the observatory will be nearly 13 meters long, approximately the length of a tour bus.
Its dry mass is approximately 8,000 kilograms, making Roman a substantial machine built for precision.
Millions of components were assembled and tested to survive launch and operate far beyond the moon.
In July 2026, technicians completed loading approximately 290 gallons of hydrazine fuel into the observatory. The current plan sends Roman into space aboard a Falcon Heavy from Kennedy Space Center's Launch Complex 39A. At liftoff, 3 powerful booster cores will begin carrying the observatory away from Earth. During ascent, a protective fairing will shield Roman from aerodynamic pressure, vibration, and intense atmospheric heating. After separating from the rocket, Roman must begin an automated sequence that cannot easily be repaired by astronauts.
Approximately 5 hours after launch, its solar panels and sunshade are scheduled to deploy.
2 days later, the high-gain antenna should deploy, establishing the observatory's powerful data connection with Earth. Roman's destination is Sun-Earth Lagrange Point 2, known simply as L2. L2 lies approximately 1 million miles from Earth, around 4 times farther away than the Moon. There, gravity and orbital motion allow the observatory to remain aligned with Earth while using relatively little fuel. This distant position provides stable temperatures and a broad, largely unobstructed view of deep space. Its primary mission is planned to last 5 years, with the spacecraft designed to support 5 additional years.
Roman carries 2 major instruments, beginning with the enormous Wide Field Instrument.
18 sensitive detectors combine to create a near-infrared camera containing nearly 300 million pixels. Each image will capture a patch of sky larger than the full moon appears from Earth. A Hubble infrared image would occupy only a tiny fraction of Roman's enormous view. In 5 years, Roman could image more than 50 times as much sky as Hubble covered in 30. The observatory is expected to transmit approximately 1.4 terabytes of raw scientific data every day. Across the primary mission, processed observations could total approximately 20 petabytes. NASA plans to release the data publicly after processing, without an exclusive access period.
That combination of sharp detail and enormous coverage is the key to Roman's scientific power.
Much of the universe is controlled by 2 things we cannot directly see: dark matter, and dark energy. Dark matter does not emit light, yet its gravity helps hold galaxies and galaxy clusters together. Its presence can be detected because mass bends space-time and changes the path traveled by light. Roman will measure a delicate effect called weak gravitational lensing across hundreds of millions of galaxies.
Those tiny distortions will help astronomers construct a three-dimensional map of matter across cosmic history.
Dark energy presents a different mystery. The universe's expansion is accelerating instead of gradually slowing down. Something appears to be pushing distant galaxies apart, but scientists still do not understand its nature. Roman will observe thousands of Type 1a supernovae, explosions whose brightness can reveal cosmic distances. Astronomers can compare those distances with each galaxy's redshift to reconstruct how expansion changed over time.
Roman will also search for the ancient imprint of sound waves that traveled through the young universe.
Together, these independent methods may reveal whether dark energy remains constant or evolves with time.
Roman's second great search will look inward, hunting planets throughout our own galaxy.
One method watches for transits, the slight dimming produced when a planet crosses in front of its star. Scientists estimate that Roman's enormous dataset could reveal around 100,000 transiting planets. Roman will also exploit gravitational microlensing, when one star briefly magnifies the light of another. A planet orbiting the foreground star can leave its own brief signature inside that magnification. Roman will monitor hundreds of millions of stars, searching for alignments that may last only hours.
The microlensing survey is expected to discover thousands of planets, including worlds that existing methods frequently miss.
Its sensitivity could reveal analogs of every planet in our solar system except Mercury. Roman may also discover rogue planets, worlds expelled from their systems and wandering alone through the galaxy. The same method could expose isolated black holes that otherwise remain completely dark. Roman's second instrument is a technology demonstration called the coronagraph. Its purpose is to suppress overwhelming starlight so the much fainter light of an orbiting planet can emerge. The system combines specialized masks, prisms, detectors, and mirrors capable of changing their shape. Thousands of microscopic adjustments will correct distortions and cancel unwanted starlight while Roman observes. For the first time, Roman may photograph older and colder giant planets in reflected visible light. It could also reveal dusty planet-forming disks and Jupiter-like worlds hidden beside nearby stars. Roman is not designed to photograph another Earth, but it will test technology needed for that future goal. Its success could help prepare future observatories to image Earth-like worlds and search their atmospheres for signs of life.
Roman's largest wide-area survey is expected to examine light from more than 1 billion galaxies.
Another survey could uncover around 100,000 cosmic explosions and rapidly changing objects. Among them may be tidal disruption events, stars torn apart after wandering too close to black holes. Thousands of exploding stars will serve both as individual discoveries and as measurements of cosmic expansion.
A separate galactic plane survey could map as many as 20 billion stars in only 29 observing days. Roman may even detect starquakes inside approximately 1 million giant stars, revealing their structures and ages.
Its archives will contain nebulae, stellar streams, cosmic voids, and perhaps phenomena nobody planned to find.
Roman is not replacing Hubble or James Webb. The three observatories are designed to complement one another. Roman can discover rare targets across enormous areas, while Webb examines selected objects in much greater detail.
Combining Roman with Euclid and the Rubin Observatory will create a richer view across multiple wavelengths.
Because every survey contains countless objects, the same observations could support thousands of completely different investigations. The most important discovery may be something scientists do not yet know they should search for.
But first, the observatory must survive launch, deploy successfully, and complete months of careful commissioning.
Within the first 5 hours, power generation and thermal protection must begin working as designed.
The coronagraph is scheduled to activate during the first week, beginning its initial health checks.
Approximately 3 weeks after launch, the wide-field instrument should power on and complete its first checkout.
Over the following months, engineers will align, focus, and calibrate the observatory's optics and instruments.
NASA expects to release Roman's first-look observations approximately 3 months after launch.
Launch dates can move, and every rocket mission faces weather, technical, and scheduling uncertainties.
Even after a successful launch, Roman will not begin delivering major discoveries immediately.
Its true achievement will emerge over years, as millions of observations become a new map of the universe.
From invisible matter to undiscovered worlds, Roman was built to expose what narrower views have allowed us to miss. Subscribe to Sky Through Time as we follow Roman's launch and the discoveries that may follow.
Hubble taught humanity to look deeply. Roman will teach us what becomes visible when we finally look wide.